for the invitation. I really enjoyed the conference. And today I want to talk about the group action, not one single diffeomorphism. So usually I state my theorem at the end of the talk, but today I will start with my theorem right after one motivation, because we are all hungry, so at least I want to show you the statement early. So if you ever think about the group gamma, discrete or continuous, if you think about the continuous group, I think this is the whole course, mini course about the G action. But today I want to talk about the discrete group. And then if you think about the group action into the manifold, let's just think about the C infinity diffeomorphism. And let's say M is just closed manifold. And always, if you have a group action, then I want to ask something like, the first question is that, what is gamma? So if you have some group action, then can we say something about gamma? And given alpha, maybe we can ask same thing for the manifold itself. Or even maybe can you classify everything? So these are usual questions when you have a group action, and I think the geometric group theory people think about these kind of questions, and then they deduce lots of properties on the group and the space that group acts. So here's the one theorem joined with Aaron Brown and myself. So the statement is the following. So let's say gamma is inside in SLNR with n is only 3. I will let you know why do we care about this kind of group very soon. And then let's say this is a lattice. That means that gamma is a discrete group in SLNR and has finite covolume. And then now let's say M is a closed manifold. And let's just assume that the dimension of M is n, which is the same n here. And now, if I have a group action from gamma to M, and I do not assume any kind of measure assumption here, and then if there exists one element in gamma such that the topological entropy of alpha of gamma naught is positive. So we have sort of this kind of group action. So we are in this setting. We have some group and we have some group action. And then now I want to answer these two questions. So first, then gamma is actually SLNZ of the finite index and then conjugation. So sometimes it is called gamma is absolutely commensurable, or what is it? Yeah, somehow commensurable with SLNZ. So we can say something about if you have some action with dynamical assumptions, then you can characterize the group. And also, moreover, if for some technical reason I want to assume that n is n less 4, then I want to answer the second question. Moreover, if n is n less 4, then there exists open set in M. I cannot really characterize the manifold yet, but at least I can say that there is an open set such that U is homeomorphic to the entropy minus finite point, or there is actually one more possibility, which is the infratoric. This is just entropy minus plus minus mod plus minus identity. There is a symmetry on entropy you can connect by identity and negative identity. So this is the degree, what is it? Entropy is degree 2 cover of this n minus finite point, and f is finite. So I can answer the first question and the second question in some sense. And of course, you can ask the last question, can you classify action on this setting? And then I will say a little bit at the end. But now if you see this question, maybe you can ask that why do you care about this kind of lattice? And then what's the motivation? Why do you care about this kind of group action? But at least, do you have any questions? Yes? Yeah, let's say, yeah, so yes and no. So right now, I do not require any kind of dynamics, something like that. This is gamma invariant or something like that. So let's say this is just some open set which can see the torus part. That's all that's all I want to claim right now. Other questions?
Is finite union of such open sets dense? Can you prove this, or is it?
No. Yeah, we don't know that. Yeah. So yeah, a priori you can be very, very small. Yeah. That will show up at the end of the talk. So yeah, probably you can ask a lot on the open set, but I will show you how open set we can get, and then what kind of thing we can say a little bit outside of the U if it's possible. Yeah, if time permits. Okay, so before going further, let's do some motivation. Why do we care about this kind of group and this kind of group action? So I was not in the first week, so maybe this is overlapped with the mini course, but it's good to review. So the entire motivation, at least for me, starts from the Margulis's theorem. So what is Margulis's theorem? Of course, yeah, it's a little bit hard to give you the example of lattice other than SL and Z. You can easily believe that SL and Z is a lattice in SL and R, which is discrete and finite covolume. But it's somehow quite difficult to give an easy example of the lattice in SL and R. But as I said that this is a theorem, there are many lattices. There are infinitely many lattices up to conjugation. But I will not focus on other lattices. I will only focus on the SL and Z. Let's say gamma is SL and Z, and n is only 3. Then if you see this theorem, then I have basically representation. I know that this is dynamics conference, but yeah, this is a representation into the infinite dimensional Lie group. But Margulis's theorem, which is called the Schper-rigidity, says that if you have, let's say, GL-MR, this is the finite dimensional Lie group. So if you have a representation into the finite dimensional Lie group, then of the finite index, so I will very not rigorous on the finite index stuff. So let's just ignore the finite index. There is a homomorphism from the SL and R to GL-MR such that if you restrict to your homomorphism from ambient group to the gamma, then this is exactly the same as rho. So this is quite surprising in some sense, because if you have some discrete subgroup in SL and R, if you have a representation, then there is no reason you can upgrade to the entire, there's no reason to be upgraded to the envelope. However, sort of higher rank property here, n is n3, allow you to extend your group homomorphism into the envelope. So one remark is that when gamma equals SL to Z, the Margulis's Schper-rigidity is false. As you expected, because SL to Z is more or less free group. So free group, you can cook up very lots of homomorphism. And for instance, if your gamma is surface group, then now people study what kind of homomorphism is good. But we cannot expect this kind of nice theorem. And also, if you think about this theorem, then actually this can be translated into the, what is it? The group action language, which is that, so for instance, if, let's say gamma is SLNZ with n is only 3, and if you think about the gamma action on M tori by tora automorphism, so having the tora automorphism action from gamma is equivalent to saying that you have a homomorphism from rho. You have a homomorphism rho from gamma to automorphism group of tori. And this is more or less SL or GL, or yeah, SLMZ up to some finite index again. So basically this is inside in SLMR, right? So Magleitch superrigidity will tell you that in the linear action, so Magleitch can tell you that says that we can classify linear action, linear actions on tori, right? So this is the one motivation why do we want to think about the nonlinear action. And maybe we hope that we have very nice theorem like this when we change the target to the diffeomorphism group. And that was the Zimmer's idea, and it was known by Zimmer's conjecture for the low-dimensional case. Because if you think about this theorem, there are two remarks. One is that if M is very, very small compared to the N here, then if I have a homomorphism from SLNZ to here, but now M is very small, and if you use the Magleitch theorem, then you have a extended homomorphism from the SLNR. And if M is very, very small, then you cannot have a, then there is no non-trivial homomorphism from SL and R to GL MR, right? Because if you have a SL 1000R to GL to R, then this is not possible. So that means that for every homomorphism from gamma SL and Z to GLMR is trivial. Trivial means that it has finite image. So that was the Zimmer's conjecture. The analog in the nonlinear action is the Zimmer's conjecture, and now is this theorem by Brown, Fisher, Hurtado. So let's say gamma is SL and Z. Again, n is only 3. And if you have a, I don't want to, in this theorem, C infinity is really important. But in their theorem, C infinity is not really, C1 is also true by Daniela, Aaron, and Jian, I guess. So, but now let's just focus only on the C infinity. M, and the dimension of M is M most M minus 2. Then alpha of gamma is finite. So let me give you, this is a, yeah, I'm not sure, but this is known for 2016, but now I think they published in 24 or, yeah, so between there, they have 3 papers. And I think the second one covers this one. And also if you assume that dimension m is m-1 with an alpha preserved the volume, let's say moreover, if the same thing, the same conclusion holds. Yes? This complement of U is N-4, yeah. This is for N-4. I believe this is still true, but yeah, there is some technical things we cannot really run the argument to get this. So, but yeah, that's because we had some technical issue, but I believe this is still true. Yeah. Yeah, this is not about the dynamics. This is the technical issue is about the structure of the lattice. So, yeah, at least yeah, the statement that the lattice should be SL3Z in the case, we can do it different ways. So, even in the statement for lattice should be SL3Z, we should do a different way because SL3R is quite small in some sense. So yeah, let's just ignore right now. Any other questions? So this was original Zimmer's conjecture, and then this is known for SL and R and many other Lie groups right now. And here, actually, what they do is that indeed they found a smooth Riemannian metric G on M such that your alpha should factor through the isometric group. And then now, if you think about the isometric group of the manifold, which is the compact manifold, so if you think about the compact isometric group of the compact manifold for some Riemannian metric, then this is a finite dimensional Lie group. So this can be embedded into some GLMR, but if you see the theorem, I should be able to extend your group homomorphism to the SLNR, but you can see that there is no non-trivial homomorphism from SLNR to the compact group, right? So this will give you the finiteness of the image. So basically, alpha is trivial. Good. So, but now. Now we know that in the low-dimensional case, what is possibility? The low-dimensional case, there is no interesting dynamics. But again, we are not satisfied yet. This is a very nice result. But we may ask the very ambitious question. If you see the Maglucci theorem, then one can ask that this kind of homomorphism is not really just random homomorphism. This is really somehow structured. So every homomorphism should be extended to the SLNR, and we know how to classify the representation of SLNR using the Lie algebra. So there is an algebraic reason why we can classify all the homomorphism from gamma to GLMR. So maybe we can ask that if you have let's say gamma is again SL and Z, with n is only 3, and M is any closed manifold. then we may ask that, can we really have the entire picture? So is alpha built by first? As you see here, maybe there is some isometric part. So that one I don't want to control. I want to think about it as an error term. So maybe there is some isometric action, which is, I don't want to think about it as some nice structured one. This is somehow error term. But second, maybe we can ask that, can we classify the action using some algebraic tool? So I want to say that algebraic action and whatever algebraic action means. And recently there is another theorem in this direction by Aaron, Federico, and Wang. They said the following. So now here it's good. It's good. And then now we want to move the next step, which is what is the algebraic action? And then if you want to say something is algebraic action, then we should be able to say the manifold is somehow homogeneous manifold, right? So how can you build a homogeneous structure on the manifold? I think that's the course mini course, and also Aaron and Federico's mini course. Everything is about some building the homogeneous structure. So, and here, actually, they really can build a homogeneous structure when, let's say, gamma is SLNZ again, n is only 3. And if you have a homomorphism from gamma to the C infinity homomorphism, and if dimension of M is exactly same as M minus 1. But now, as you see here, if you see that if your action preserves the volume, then we know that it is trivial. So there is a possibility that either first, alpha of gamma is finite. This is possible, as in the isometric action. And now, I will write down alpha is projective up to smooth conjugation. Projective action, especially, I will let you know what it is, but especially M is diffeomorphic to sphere, M minus 1 sphere, or RP M minus 1. So I said that the algebraic action with the quotient mark, but let me know one example that should be, let me give you two examples that should be algebraic. And one of them is the projective action. So example is that, let's say, gamma is SLNZ again. For defining projective action, I don't need n is n3, but let's just think about any n or n is n3, and then this can act on Rm by matrix multiplication. So I emphasize that this is given by the matrix multiplication. If you have a vector, a matrix, and if you have a vector, then this is given by just matrix multiplication. And I don't know what this algebraic action really should be, but at least I know that matrix multiplication should be algebraic. And also, this will, because this is not a compact manifold, so I want to induce the actions to the space of lines. In other words, this is exactly RPM minus 1. Right? Because your linear action preserves the line to line. So this is one possibility of the algebraic action, one model. And also, if you do not like the unorientable manifold, maybe you can go to the space of rays in Rn. And this is exactly as n-1, the n-1 sphere, right? And these two actions coming from the matrix multiplication is called the projective action. So whatever algebraic action means, this kind of example should be algebraic. And they really show that either your alpha is isometric or finite, or your manifold has homogeneous structure, and your action is smoothly conjugate to the algebraic action. So now I think this kind of question is now called the Zimmer program. And I think now the main theme of the program is about how can you build a homogeneous structure on the manifold. And the theorem I wrote with Aaron, I already raised it, but about the open set, that's also one example of building the homogeneous structure. We cannot really classify yet, but at least we can build some homogeneous structure on some open set. Any questions so far? So let's see. So now, in terms of dynamics, we saw so far isometric action and projective action here. But if you think about the isometric action is boring. That one I can see. Especially if it is finite, then there is no dynamics. Everything is fixed up to finite index. But projective action is also somehow non-chaotic. So here, if you think about the projective action, then this is non-chaotic. Especially every element in gamma has zero topological entropy, right? That means that your path determines the future. So actually, the dimension n, there is a chaotic dynamics, you can see. This is only for SL and Z. And if you think about the SL and Z action on n tori, even though I already mentioned the Tora automorphism, let me just say that what it is here. So if you think about the gamma action on n tori, which is Rm mod Zn, by again the matrix multiplication, if you have a vector on here, and if you have matrix on here, then the action by A on this vector is given by just matrix multiplication. And here, this is called the Tora automorphism. And this one has many of diffeomorphism. Especially it contains many positive topological entropy element. So I like positive entropy, so maybe one can ask that, can you build some homogeneous structure when you have a positive entropy element? So, but before that, this is beyond uniform hyperbolicity, so maybe it is a good idea to think about the uniform hyperbolicity case first, right? If you want to consider the positive entropy case, then the easiest, at least for me, the easiest one I can deal with is the Anosov diffeomorphism. So actually, I did deal with the Anosov diffeomorphism first. I think this is 2024 or 2022. So as a part of my thesis, actually I did the following. So let's say gamma is inside in SLNR again, and is LS3, and lattice. Then if you have a action on M, which is dimension n, and in here I should assume the volume preserving, and not really the positive topological entropy, but if there exists gamma knot in gamma such that alpha of gamma knot is anosov diffeomorphism. And actually, I even can do this with the partially hyperbolic diffeomorphism, but let's just assume that there is one anosov diffeomorphism element. Then I can actually say that M is diffeomorphic to the tori. And alpha is smoothly conjugate to the tori automorphism. So this is the uniform hyperbolicity setting. But this is somehow, in some sense, this is quite soft. The argument is quite soft compared to the theorem I mentioned in the beginning with Aaron. Because the idea is basically, I have an invariant measure. So if you think about the, here as a conclusion also gamma should be SLNZ up to finite index and up to a conjugation. So in here I have an invariant measure. But if you think about the gamma lattice in SLNR, then it is known that this is not amenable. And that means that there is no reason we have an invariant measure. Especially we do not need to have a nice invariant measure on the manifold. There's no reason. But if you assume that, then what can we do is that anosov diffeomorphism will give you the continuous splitting into the stable and unstable, right? So anosov diffeomorphism will give you the continuous splitting on the tangent bundle level. And fortunately, from here, actually Zimmer already told us that so-called Zimmer's cocycle superigidity, Zimmer solved the cocycle problem for the gamma action. So Zimmer can solve measurable solution of the cocycle, the derivative cocycle gamma times m to the, let's say, S, L, and R, which is the derivative cocycle. So if you assume the volume preserving, then I know the measurable solution from the Zimmer. And here I also know that the continuous solution, continuous splitting at least, from the anosov diffeomorphism. And then I can compare them. And because you can expect that the continuous splitting is basically same, it should be same as the measurable splitting from here. The solution means that this derivative cocycle comes from the representation. So you can detect the stable and unstable from the measurable solution given by Zimmer. So I can compare them, and then you can match that so that you actually can solve the derivative cocycle in the continuous, as a continuous cocycle. So you have a continuous solution. So you can build many anosov element, and then especially codimensional anosov diffeomorphism that will give you the torus structure. But now the problem, or the problem, what is it? The real question is that, and actually this is the part Aaron asked me a few years before, and then that's the starting point of our work. Can you drop the volume preserving? Because again, gamma is not amenable, so there's no reason that we have the gamma invariant measure even. And especially if you think about the projective action, then there's no gamma invariant measure at all. I think this is a really good exercise for students. If you do not see this before, then I think it's a good idea to think about the gamma action on RPM-1 or SM-1, and then can you find the gamma invariant measure? But it's not possible. So here's the actual theorem that from the uniform hyperbolicity to the non-uniform hyperbolicity. Again, if you have SLNR with n is only 3 lattice, for again the technical issue. But now if you have, I want to drop the volume preserving now. but still the dimension of M is n. The reason I thought, the reason I'm thinking about the dimension M equals n is that this is the first case you can see some positive entropy element. And of course, I don't want to claim that the dimension n is the end of the world. There should be some analog in higher dimension. But we also have some statement about the higher dimensional setting, but this is not really clear. So I just want to stick with the dimension m equals n. And then now if there exists gamma naught in gamma such that if you have a positive topological entropy, so now I'm really on the non-uniform hyperbolicity, then actually the main theorem for us is that one of the main theorem for us is that there exists alpha of gamma, again up to finite index, but you can upgrade to the entire gamma, alpha of gamma invariant probability measure mu that is absolutely continuous. So this is the game of measure rigidity. So it is a similar or flavor, but a little bit different mechanism to upgrade your measure as in the Aaron and Federico's mini course. This is more higher rank phenomena. But still, there is a measure rigid game here. I can upgrade. If I have time, then I may say a little bit about the proof. But again, we need to build the invariant probability measure. And also, it should be it is absolutely continuous. So there is a measure rigid game in here. And also, if you have M with the measure, then this is now the measure space. There exists measurable isomorphism to tori with the Lebesgue and or whatever infratori means, but let's just forget a little bit, but there is a possibility. You should go to double cover if you see this, but there is a measurable isomorphism. And here you have a gamma action by alpha. And here I have a gamma action by rho for some rho from gamma to the automorphism. And because the measure itself is absolutely continuous, this is the source of the open set U. So that again, we don't know that mu is fully supported. We don't know that how much your support is big enough in the M. So we cannot say anything about really how large U is in this case. But at least measurably, we have a conjugacy. So we have a sort of measurable homogeneous structure on the manifold. Yes? Yes, sorry. Yeah, for one element. Only for one element. No, I don't think so. Yeah, we did not think about that. In the proof, that is not helpful, at least for us. Having more than one element that has positive entropy looks like not helpful in our proof. So, yeah, I don't know. Maybe it is helpful. Maybe if you assume that there are many positive topological entropy, then maybe it is helpful, but I'm not sure. Yeah, at least in our proof, we cannot really use many elements. We really only use the one element, and then I think at least right now I cannot see that many elements can be helpful or not. But yeah, we did not think in that direction so far. Yes. Measurable bijection. So up to null set, there is a full measure set, and they are bijection, and the measure mu goes to the Lebesgue. Thank you. And that's the reason why I drew the big circle here. So H commute, yes. H, if you go alpha of gamma first, then you got the rho of gamma with H for all gamma in gamma up to finite index again. Thank you. Yes, every standard probability spaces are all same. Yes, finite index. And I think I have around 10 minutes. So before saying something about the proof, let me do it. What is the real expectation on the dimension n case? So now it looks like this is a conjecture. So let's say gamma is the SLNR. Inside n is less 3 and the lattice. And either if you have a group action on the manifold and the dimension is n, then either first, second, or third. First, maybe you have a finite action, of course. And or alpha extends to G action. Or gamma should be SLNZ. So I believe that the positive entropy only happens on here. And then gamma is SLNZ up to finite index and conjugation. And the alpha is combination of, so alpha is coming from the, let's say, Katok-Lewis blow up over Katok-Lewis blow up, or some, let's say this way. So sort of alpha can be built by Tor automorphism. On tori. So I expect that because there is a projective action times S1. So something like RPM minus 1 times S1, you can act on there simply by product action. But that does not have positive entropy. So probably, yeah, this is the only possibility that you can have the positive entropy. And let me give you one example. You may be very disappointed because it looks like not algebraic, but I want to consider it as a algebraic action. So why I did not say that alpha is just the Tor automorphism? Because there is an example by Katok and Lewis. And recently, David Fisher and Karim Malik, but I only want to introduce the Katok and Lewis blow-up example. So if you have SL and Z action on n tori, so you can think about SL to Z in this case. But here is the n tori and by Tor automorphism. And 0 is the fixed point. This is just matrix multiplication. So 0 is the fixed point. But then now what I want to do is that you have a lines on, locally there are lots of lines on here. And then if you see the lines intersect at the one point, then algebraic geometry people want to do the blow up. So here I have RP n minus 1, which parameterize the lines through the origin. And then now I want to think about the lines on here. So I only want to remove the fixed point, and then instead of the fixed point, I want to put the RPM minus 1, and then think about the lines through the origin in the lines in the RPM minus 1, as RPM minus 1 is the parameterization of the lines. So then now you can think about another topological space X that's subject to the n tori. Outside of this weird RPM minus 1, it is 1-to-1. But here I have an entire RPM minus 1 goes to the origin. So maybe it looks like this is very horrible space, but indeed, actually, X is, you can make the alpha gamma action on X, which is C omega even, let's say C infinity, action with invariant volume form basically, but it may be non-orientable, so non-vanishing density form. So actually, Kato and Ruiz realized that the action on the blow-up space has very nice property. This is infinite, and basically it preserves the volume. And outside of this RPM-1, there is a one-to-one correspondence to the tori. So outside of this RPM-1, your action is basically tori automorphism. So you have lots of topological entropy. And on here, you have a projective action. So yeah, I don't know. I want to consider this as an algebraic example, but maybe you don't agree. But I don't know. So that's the reason I said that in SLNZ, your action can be built from the tori automorphism. And let me say a few words in the proof of this. I think so, yeah. So here, the idea of proof is the following. So because I have a positive topological entropy, one positive topological entropy. So now I have a suspension, so which is that M alpha is, you can, because I don't like the discrete group, okay, I like the discrete group action, but it is better to have a continuous group action. So G is SLNR, and gamma is just a lattice. So I can make the suspension, if you see the diffeomorphism, then you can make the flow using the root function. So basically, same thing happens on here, and there is a M alpha on here, and then fibers are M. And now, because the existence of gamma naught with the positive topological entropy, because we know the variational principle, so there exists mu naught, which is alpha of gamma naught invariant, and the metric entropy is positive. So what I want to do is that in the suspension, I just want to think about one fiber, and then let's say this is gamma naught. Let's just say that gamma naught is the curve on the G mod gamma. And then now if you think about the fiber dynamics on here, if your gamma naught fixed the identity coset, then you have a fiber dynamics as the suspension. So if you think about the gamma naught in here, and then if you think about the alpha tilde, let's say G act on M alpha by the suspended action, and then alpha tilde gamma on the fiber over the identity coset is exactly the same as the alpha of gamma naught. So what I want to really do is that there exists measure mu naught tilde on M alpha such that the fiber-wise entropy, whatever it means, is positive. So fibered over the fibers are all M, so if you conditioned on the projection to G mod gamma, then you have a positive entropy. So this is the way we use the positive topological entropy element. So I'm not sure how can we use the multiple topological entropy positive topological entropy element in this scheme. But then now what I want to do is that I just want to upgrade this measure to the entire space. And in here I need to, because I only have a Dirac delta mass on identity coset and then some weird measure on the one fiber. And then I want to average a lot so that we can get the G invariant, absolutely continuous measure mu tilde on M alpha, and this is enough to deduce the gamma invariant absolutely continuous on the measure. But here, we need two things. We should be able to average the measure and then take the Wigstad limit. So, but I want to keep the positive entropy. So I need to know the how centralizer looks like, and that's the algebra comes in. So arithmeticity, so-called arithmeticity involves on here, because you are lattice, and your lattice has some structure. So some group structure we can use in here, but also we need to use the fact that the upper semi-continuity of the fiber-wise entropy. And that's the Yomden-Neuhaus theory. Fiber-wise Yomden-Neuhaus theory appears on here. Yomdin and Yox. Fiberwise version, because I want to say that the fiberwise entropy is upper semi-continuous. And now I have a 30 seconds. I want to use only 30 seconds. So we can deal with the positive entropy case. And actually, Aaron, Federic, and Jiren, did I write down the Aaron, Federic, and Jiren? I think I missed, okay, I forgot. The dimension n-1 case, they classify the dimension n-1 case, and actually they can show that on volume preserving case in dimension n, you can control the measure with the p-invariant measure with positive exponent. So we know how can deal with the positive exponent and positive entropy measure. But we don't know really right now is that how can you deal with the zero entropy measure or zero exponent measure. That's the really mysterious one. So probably we can say something about the structure if you assume the positive entropy and then something, then we may be able to, we are working on how your boundary of U looks like. But one chunk, maybe your action is somehow just zero exponent, volume preserving. So then in that case, we cannot say anything. So that's still mysterious. And of course, other than this dimension n case, there are lots of nice open questions. So I'm very happy to talk about it. And I think I'm out of time. So I'm stuck here. Thank you.
Any questions?
So you have this measurable isomorphism, but in the conclusion of your theorem, you say you get an open set.
Yep.
So how do you get an open set from a measurable isomorphism?
So that one, actually, Katok and Rodriguez-Hurst has similar thing for the z to the n-1 action. So in there, they basically, when you build a torus structure, this measurable isomorphism is not really just measurable. You have some regularity along some nice directions. So that's the way they can build. And then our job in here is that from the z to the n-1, your gamma is bigger group. So we should work with some unipotent elements and stuff like that. So yeah, in there, the short answer is that your measurable isomorphism is not really just measurable. You have some regularity along some nice foliations. So that's the way, yeah.
There it is. One other question. So when you have an Asaf, you can use your previous theorem with one Asaf element to get that it's actually smoothly conjugate. Do you think the same is true for a dominated splitting, if you have a dominated splitting?
That's actually what I did.
Oh,
yeah,
okay.
Yeah. Actually, my assumption on the previous theorem is that dominated splitting, volume preserving, dimension n, I think. Yeah, I think that's all. Yeah, so yeah, my previous theorem is really assuming the dominated splitting.
Okay, any other questions? Where are you?
Excuse me, when you said the projective action in the homogeneous space, you said that it's almost rigid. So all have zero topological entropy.
Yes.
Do you know if there are some information about some slow entropy or polynomial entropy of this?
Oh, that's a good question. And the short answer should be, I don't know. Yeah, sorry, yeah. But yeah, I think that's the good, yeah. So because I think that, yeah, maybe the right question is that if you assume some other kind of dynamical invariant for the group action, then can you say something more? Still, I think really lots of things are still open. So yeah, I don't know.
Okay, thank you.
Yeah.
Okay, any other questions? Okay, then if not, let's thank Homin again.
Thank you.